Okay, good evening. I really like your costumes. Tonight, well, to start with, I'm Todd Morrison. I'm the director of Las Cumbres Observatory. We are a nonprofit corporation. We're based in Goleta. We've built and we now operate a global network of telescopes for astronomy, science, research, and education. We have an outreach, a public outreach program, of which this is a part, this public talk. We do about 4 of these a year. We also have a couple of other things I just wanted to mention. So first, let me go back to the talk. Typically, they're 3 months apart, but by coincidence, we have one that's a week from today. And that's going to be Andrea Getz from UCLA, who's going to be talking about, her title is something like The Monster at the Center of the Galaxy. It's about the supermassive black hole, which is a monster in the sense that it's eating everything nearby in the center of the galaxy. So that's a week from tonight here. We have a Astronomy on Tap, which is once a month roughly at the Matrix Bar down on Lower State Street, and the next one of those is December 5th. And we occasionally have open houses at our facility in Goleta. Probably some of you have been to that. Those are always a lot of fun. You can walk around among the telescopes that we're building and talk to the engineers and the astronomers, and we usually serve refreshments at that too. It's kind of a pleasant thing. You can find out about all of the upcoming events on our website. And dates are not set for the things next year, but there will be sort of the same number of things next year as there have been this year. So tonight, it is my great pleasure to introduce Dr. David Spergel. Dr. Spergel is one of those people who has so many accomplishments that I had to kind of pick and choose what I was going to tell you about, because if I fit them all in, you wouldn't have time to talk. He was educated at Princeton and Harvard. He's won a number of prizes, the Breakthrough Prize, the Heinemann Prize, which is given jointly by the American Astronomical Society and the American Physical Society. He has won the Gruber Prize, a MacArthur Fellowship, the Genius Award, the Warner Prize from the AAS. He holds joint appointments to the Princeton faculty, and he's also the director of the Center for Computational Astrophysics at the Flatiron Institute. So this is a science institute that is in the process of being built. It's funded by Jim Simons in New York. It's in a building nearby the Flatiron building. It's a spectacular place. I had the pleasure of visiting him there a few weeks ago, and I think that there are going to be great things coming out of this new science institute. The plan for tonight is Dr. Spergel is going to talk, answer questions, roughly an hour, and then he'll be outside to chat further if you're interested. So his talk tonight is, whoops, I lost it, is Our Simple, Strange Universe. Simple in that it's defined by a few numbers, strange in that despite that fact, we don't know what most of it is. Dr. Spergel.
So Todd's basically summarized my talk. That's the basic message I want you to leave with. But since, I thought I'd fill in a few details on that picture and tell you how we got there. And it's been a really fun journey to be part of this discovery of how remarkably simple the universe is. So with its simplicity, we've seen that a very basic model with a handful of numbers fit all of our observations. And we start with sort of the simplest, or almost all of our observations, and I'll get to it towards the end of the talk. Start with the idea that the laws of physics we see in the laboratory that apply in this room are valid across the whole visible universe, are valid across time. We start with the idea that the universe is geometry, and we'll talk a little bit more about that. It's as simple as it could be. The Euclidean geometry that Mrs. Smith taught you in 8th grade, some of the angles of a triangle is 180 degrees, is valid not just on your 8th grade test, but on the scale of the visible universe. And that the basic properties of the universe is characterized by 5 numbers. The age of the universe, which is measured to precision to be about 13.8 billion years. We know that with an uncertainty of only 1%. The density of atoms in the universe, which we've measured to better than 1%. The density of matter, how lumpy the universe is, and how that lumpiness varies with scale. And with those 5 basic numbers, we fit everything we see. The observations of the leftover heat from the Big Bang, the microwave background, observations of the large-scale distribution of galaxies, abundance of elements, the properties of distant supernova explosions we see with the Hubble telescope and smaller telescopes looking at ground-based telescopes looking at the nearby universe. All the pieces seem to fit together with these 5 numbers. But it's a universe that is also remarkably strange. Atoms, the stuff that makes up us, the chairs, everything around us that we see, makes up only about 5% of the universe. The next 25%, most of the mass of the galaxy, is in the form of something that we call dark matter. That's just a name we give it. We don't know what it is. We know whatever it is, it clusters in galaxies, so it feels gravity. It clusters together, it's clustered in galaxies. We see it in the large-scale structure of the universe. We know it doesn't interact with atoms much, or we would have sensed it. We know it doesn't interact with light much, almost not at all. So we call it dark. The ideas we have for what it might be vary from subatomic particles that we haven't seen yet to black holes moving through space. And that's the stuff we understand best. The next part of the universe, about 75%, seems to be energy associated with empty space, what we call dark energy. And this is the dominant form of energy in the universe. And we only sense it through its effects on the overall expansion of the universe. The universe is behaving as if space itself is filled with some stuff that affects how it evolves. And if our current understanding is correct, this dark energy will determine the eventual fate of the universe. So this is kind of big stuff that we don't understand. It's kind of a, one hand you stand here and you say, no, we understand a lot. 5 numbers, we fit everything. But we're also in a state where the universe is mostly mysterious and filled with darkness, which is why I thought this was such an appropriate topic for tonight. So to understand the picture of how we got there, I have to begin by first teaching you some physics. I'm going to begin by teaching you special relativity. The key idea in special relativity for this talk is light travels at a finite speed. It takes light a few nanoseconds, a few billionths of a second, to get from me to you. So you're not seeing me as I am, but as I was a few nanoseconds ago. That's not that relevant usually. I don't change that much on the nanosecond time scale. But if you go look at the sun, it takes light about 8 minutes to get from the sun to us. So we see the sun as it was 8 minutes ago. And the further out you go in space, the longer it takes light or radio waves, form of light, to travel. How many of you have seen the movie The Martian? It's excellent. If you haven't seen it, I really recommend it. It really captures a lot of realistic parts of traveling to Mars and what it would involve. The opening scene about the wind isn't right, but besides that, it's all pretty great. And one of the things it captures is how long it takes for information to get from here to Mars and back, right? They send the message, and they sit and they wait. You know, and they think it's in a position where it's almost an hour for them to ask a question, and then to get an answer. And the further out you go in space, the further away that is, and the further back you go in time. So when we say a star, the nearest star is 4 light years away, what that means is it takes light 4 years to get there, or light 4 years to get from there to here. So we see a star 4 light years away as the way it was 4 years ago. And if you were on a planet orbiting around Alpha Centauri, observing Earth, you would see us as we were 4 years ago. Go out further to a star that's 40 light years away. We're seeing them as they were 40 years ago. They see us as we were 40 years ago. I had a full head of hair then. And when we look at nearby galaxies, they might be 1 million light years away. And we see them as they were 1 million years ago. Much of my talk will focus on the microwave background. That's the leftover heat from the Big Bang. That's light that's been traveling to us for 13.8 billion years. That means the pictures I will show you will be images of what the universe looked like 13.8 billion years ago. And this is why astronomy is really a historical science. When we look at the Hubble telescope at a distant galaxy, we see them as they were 12 billion years ago. We get to see the whole evolution of the universe. All right, everyone good with special relativity? Yeah. Good. Next, we're going to move on to general relativity. As my academic great-grandfather taught me, Johnny Wheeler, general relativity consists of 2 ideas. Matter tells space how to curve, and the curvature of space tells matter and light how to move. So this is a picture that tries to illustrate this. This represents the sun, and the picture represents space curved around the sun. And this is light from a distant star at position A, traveling to us, and you see space is bent by mass. So light gets deflected. So while the star was actually behind the sun, at this position, you see the star distorted at position B. And this was something that Einstein predicted. And during a lunar eclipse in 1919, astronomers were able to test this. And this was the great confirmation of general relativity. And here's the New York Times from November 10th, 1919.
Wow.
And here we go. Front page news. This is 1919. Besides Marie Curie, mostly men of science, more or less a god, Einstein theory triumph. This is my favorite line. Stars were where they seemed, or not where they seemed or calculated to be, but no one knew where. This, of course, is the New York Times printing fake news again. Because Einstein calculated where that star was supposed to be, and his great triumph was getting that prediction right. Though actually, if you look at the history, Einstein got lucky. He first did the prediction in 1916 with an early version of general relativity that wasn't quite complete. That gave an answer that would have been off by factor 2. They looked for the effect in an eclipse in that year, maybe early 1917. The weather was bad. It wasn't observed. It was the midst of the First World War. So they didn't test the theory. Meanwhile, Einstein develops the theory more fully, gets the right prediction, and then Eddington and others goes and makes this observation. And this theory has now stood the test of 100 years, and with something we feel we can apply with confidence on the size of the universe. This then leads to a theory that's often called the Big Bang theory, but I think a better name for it is the expanding universe theory. And this is, I think, the most conceptually difficult idea that we'll talk about in the talk, because almost all of us have a kind of Galilean notion of space and time. We think of space as absolute. But what Einstein teaches us is space is relative. I should only define distances in space as distances between me and you, or distances if I tell you I can fly in, 11 hours from Los Angeles to Tokyo, and then in 10 hours from Tokyo to New York, or say Tokyo to London, and then another 8 hours to New York, and then 6 hours to LA. The fact that I gave you those distances have actually specified the shape of the Earth. So I can specify everything in terms of distances. And that's what we do in general relativity. So we specify the distances between galaxies. And what we find over time is the distances between galaxies grow. And the picture that I have in my mind of this is I suppress one dimension. I imagine all the galaxies living on the surface of a big sphere. And we're here, Andromeda is here, and every other galaxy is a position on the sphere. The radius of the sphere is time. So as the universe ages, it gets bigger, and it grows. And as the distance between objects grow larger and larger. So when you think about the universe expanding, the question I always get at talks is, what is the universe expanding into? And I think of it as expanding into the future, because it will get bigger and bigger. Now that rate of expansion isn't linear in time, but it depends on the universe's composition. Now let's take that picture seriously. If the universe is expanding as a sphere with time, what happens if we run time backwards? If we go back in time, things get closer and closer together. The universe gets denser and denser. Any radiation gets hotter and hotter, so as you compress it. So as we go back in time, things get denser and denser, hotter and hotter, till we reach this point here we call the initial singularity, where we get to an infinite density and temperature. That's when time effectively begins. And you'll notice, thinking about this collapsing sphere, the Big Bang, this moment of singularity, didn't happen at one particular place. It happened everywhere. Everywhere in the sphere collapses to that point. It did, that moment of initial singularity happened at a moment in time, but everywhere in space. Now, for purposes of our talk, we're going to get to ignore the details of what happened here, which is good, because we don't understand it. And start a few microseconds after this initial singularity, after the Big Bang, at which point the universe was very hot and dense. Watch it expand, and what we'll observe will depend on the later evolution. Now, those of you who haven't thought about this before, and those of you who thought about it before, are left with some questions at this point. What was before the Big Bang? What was here? We don't know. There are a couple different classes of answers. One answer says time begins at the Big Bang. And asking what's before the Big Bang is like asking what's north of the North Pole. It's not a well-defined question in certain ways of looking at this. In other ways of looking at it, there's theories where people say before this expanding phase, there was a contracting phase. And the universe goes through a bounce and re-expands. Others imagine this emerging from a quantum foam. But the most honest answer is we don't know. In many ways, our knowledge of physics is breaking down here. We're getting to a point at which the fact that we don't have a complete theory that combines quantum mechanics and general relativity, we don't really have a guide to tell us how to extrapolate through this point. So, what does this say about the history of our universe? We'll again start from the Big Bang and go forward. About 100 seconds after the Big Bang, most of the deuterium and helium in the universe formed. The subject of my talk, this cosmic background radiation, formed primarily about a month after the Big Bang. It's sort of the leftover heat from the Big Bang. This cosmic background radiation, by the way, is something that, looking around at the average age of this audience, most of you like me have seen. I think many of you may have remembered looking at TV before there was cable, and you turned your TV between channels and you saw static. About 1% of that static was cosmic background radiation. And if you tune your radio between channels, about 1% of the static you hear in your radio is cosmic background radiation. And this background radiation was first discovered by Penzias and Wilson at Bell Labs when they were looking to use microwaves to communicate. And they pointed their telescope all different directions, and picked up the galaxy, and they found wherever they looked, there was leftover radiation, which we now understand is this leftover heat from the Big Bang. So we have this leftover heat. An important point in our history is about 300,000 to 400,000 years after the Big Bang. At that point, the universe got cold enough. Temperature was about 3,000 degrees. Cold enough that electrons and protons were able to combine to make hydrogen. At which point the universe becomes transparent, and the radiation can move from them to us. So when we look out at the microwave sky, we're actually seeing what the universe looked like about 380,000 years after the Big Bang. And back then it was quite simple. So Penzias and Wilson were the first ones to see this uniform radiation back in about 1965. And then over the subsequent 25 years, astronomers worked hard to try to detect any fluctuations in that radiation. And that was first seen back in 1990 by COBE, 1991, a NASA mission, the Cosmic Background Explorer, that mapped the whole sky. And these figures show a map of the sky observed by COBE. And you should think of these pictures as like showing you the globe. Rather than showing the map of the Earth, I'll often show an oval, right? You've seen that. This is the sky around us. And we're showing the sky around us in a coordinate system in which the plane here is the plane of the Milky Way, our own galaxy. And this shows, if you look at the sky, what you mostly see is a uniform sky at a temperature a bit below 3 degrees Kelvin. But if you look very closely, and COBE was the first one able to do this, you see tiny variations at the level of a few millionths of a degree. So fluctuations of a part in 10 to the minus 5. It's a lot like looking at the Earth from space, where the Earth looks like a sphere from the distance. That's what you see in these pictures from the moon. When you look closely, there's mountains and valleys and variations in the surface. So with more sensitive observations, we were able to see these mountains and valleys. Now the picture's a bit more complicated than just the mountains and valleys here. You'll also notice this bright red thing across the surface here, and that's our dust in our own Milky Way, dust and electrons. In some ways, as a cosmologist, for me, this is the smudge on the window. I'm looking out and I want to see the distant scene as the stuff in front. This stuff is only, 30,000 light years away, 10,000 light years away. It's nearby. This is the interesting stuff for us, the 240 billion years. And we look at this and use this to study what's going on. The next step from space, we did some observations from the ground and advanced the field, but the next big space-based step was a satellite that I was involved in called the Wilkinson Microwave Anisotropy Probe, or WMAP, which we named after our colleague Dave Wilkinson. And to get away from contamination from the Earth, we launched this mission out to 4 times the distance to the moon to what's called the L2 point. And we sat there, so we chose that point so we can sit there with the Earth and Moon behind us, Earth and Sun behind us, and Moon as well, mapping the sky in a very clean environment. And these are the high resolution maps that we were able to make from there. And again, you see the galaxy in red, and the cosmic signal in blue. We want to separate this out. So we make the measurements at multiple frequencies. As we go up in frequency, the emission from electrons in our galaxy gets dimmer and dimmer. And then we start to pick up a signal from dust. We can combine all these observations in a way to eliminate the galaxy. And we get a very clean picture of the sky, of the universe's baby picture. And these, what you see here are variations in the temperature of the universe 13.8 billion years ago, 380,000 years after the Big Bang. And we can characterize these fluctuations, and they can tell us a lot about the history of the universe. Now, if you stare carefully at this map, something that struck me soon after we saw it is the letters SH. And what does this mean? So there's a couple possibilities. This was honoring Stephen Hawking, Saddam Hussein. The creator looked on the universe, thought poorly of it, and started to scribble something. Then she was more forgiving and stopped. I think it mostly represents human evolution. We're very good at finding patterns, even when they're not there. Our ancestors, well, imagine 2 groups of ancestors, potential ancestors. This group here, they're calm people. When they see something withering, movement in the grass, little flicker of orange, it's probably nothing, and they're usually right. This other group here, this couple here, they see this flickering in the grass, and they're panicky, nervous people. And they see patterns when they're often not there. And they're running all the time from these little flickering patterns. And 9 times out of 10, they're running for no reason. But 1 time in 10, that tiger eats that couple over there. And these people are our ancestors. And we're good at finding patterns even when they're not statistically significant. So that's why when you look at data, it's very important to be careful and do a rigorous statistical analysis. One part of our statistical analysis, and this is the results I'll mostly show you, consists of throwing down circles and asking, what's the average temperature in this circle? Throwing out another circle, average there, and look at what's the average fluctuation as a function of scale. And this looking at how lumpy the map looks like as a function of scale is how we do most of our measurements. Actually, I'm going to skip to here. And this plot shows a summary of what we actually measure, which is I take that map and I measure how lumpy it is versus angle. And these points show the measurements we made from space of lumpiness versus scale. And you can see the map as a characteristic scale of about 1 degree. And that corresponds to actually how far a sound wave could move in 380,000 years. And this gives us a measurement of the geometry of the universe. And here's measurements from ground-based experiments. This is about data now from about 10 years ago. I'll show you more recent stuff soon. And the curve shows our model going through the data. And the model does a really good job of fitting pretty complicated data. And this is the basis of this simple model I talked about earlier. And we not only can we match this data, that picture I showed you of the baby picture, we can match other things. What we like to do is we take these initial conditions, we run them forward in time in computer simulations, we predict the large-scale distribution of galaxies, and what we see in terms of its statistical properties match. And if I were to go back to 2010, we'd say all the pieces seem to fit together. But what do you do when you have data that fits the model? Well, what you want to do is go get better data. And the next step in getting better data was a European satellite called Planck. That was launched about a decade ago and reported its final results just a couple weeks ago. And the Planck Experiment, well, it's European-led, actually the key components were actually built here in California out of JPL, where they developed a lot of the detectors. And Planck took the sky and then zoomed in. And so 3 times the resolution, 10 times the sensitivity that we did with WMAP. And rather than look at 5 frequencies to remove the galaxy, they looked at 9. So you have even better control to make even a cleaner picture of the microwave sky. And here's the data from the Planck experiment. There's a couple things I want you to see here. So this is how lumpy map is versus angle. The blue points were for our experiment. They they go about this far. The white points here are for the Planck experiment. And you can see where they make where they overlap, they agree beautifully. So this is first a great experimental triumph. We're measuring fluctuations at the level of a few millionths of a degree, and we're seeing the same picture. These green and red points come from an experiment which I'm part of in Chile, and the red points are an experiment led from a group from UChicago in the South Pole. And again, you see on these smaller scales, a very consistent story. And to me, what was incredibly remarkable is we took this theory with 5 numbers, dark matter and dark energy, and we fit it through this data, and then predicted the rest. And it all fits. And this is true also of measurements of large-scale distribution of galaxies, and things like measurements not just of the temperature. So here's from the Planck team's recent paper. They fit the temperature data, and then predict what they should see in temperature and polarization, in how space is bent, gravitational lensing, and the blue curves, they've got no free parameters. You fit to the data up there, and all the pieces come together. So this looks pretty good. And it looks like all the pieces fit. The problem is now, I have to say, sort of. And that sort of arises, I can skip to this one. When we go and try to measure how fast the universe is expanding. And with the Planck data, able to make this very precise measurement of the expansion rate of the universe versus time. This is called the Hubble Parameter. And if you go back to that picture of that expanding sphere, is how fast the sphere expands versus time, what that expansion rate of the universe is. And we can measure this in a number of different ways. We can use distribution of galaxies, and that looks consistent. And quasars is mostly consistent. But the problem is when we look to measurements of our local universe and use the Hubble telescope, and this is work done by a team led by Adam Rees, who won the Nobel Prize in 2011. And that team's best measurement and other nearby measurements in the nearby universe tend to agree with this, that the expansion rate of the universe measured locally is faster than the model predicts. So this problem is one of the things that's keeping us up at night. And when you've got a problem like this, there's three possibilities. There's something wrong with the data that makes the gray curve of the way we analyze it. There's something wrong with the blue data. Or there's something wrong with the model. The most interesting possibility is that there's something wrong with the model. And the thing you'd be tempted to do is change the model so the universe's expansion rate is picking up with time. And that expansion is going faster and faster. And that's a universe in which the energy in this dark energy grows with time. And it's actually a model called the Big Rip. And one of the interesting implications of the Big Rip model is the acceleration goes faster and faster, and eventually tears apart galaxies, then tears apart atoms, then tears apart nuclei in the space itself, and eventually everything is destroyed in the whole universe. So this Big Rip is not an attractive model. Now, I was actually asked about the Big Rip model when some data came in 2016. I was interviewed by New Scientist. In just the beginning, I'd say almost exactly 2 years ago today, right? Exactly. And November 1. And I was asked what I thought of the Big Rip model. And I compared the possibility of the universe ending in the Big Rip to the Trump presidency. I said it might be consistent with some data, but I didn't think it was going to be likely to happen. But I did find it frightening. So today, I can say this in California. I gave this talk in Mississippi 2 weeks ago. I didn't use that joke. So today we wonder, is there a Big Rip? What's going on? So and it's not just that problem there, it's also looking at how lumpy the universe is. This is some data we just reported pretty recently, where we measure how lumpy the universe is versus scale. And this was our measurement in gray. And all these other groups agree with it. But the Planck team, the CM microwave background measurement, is somewhat high. Again, consistent with the direction of something like a Big Rip. So, what's going on? Is there something wrong with one of the data sets, or how they are estimates on errors? This is actually what I think is most likely. Yeah, it's very hard to do these measurements right. But the intriguing possibility is we're seeing evidence for new physics, and of course the Big Rip is just one possible interpretation. Other possibilities, we're seeing the breakdown of general relativity. That'd be pretty cool. Or there's some other new piece of physics we're missing. And the next step when you have something like this is we need more data. And what I want to describe in the rest of the talk is one piece of the story of how we're going to collect more data. There's a whole bunch of different observing efforts going on, from measuring the expansion rate of the universe more carefully, and actually talk tomorrow at the Cumbres Observatory to the staff about one of the things we're doing in that area called WFIRST. But today I want to keep with the theme of studying the microwave background and talk about how we're measuring it that way. And just say more about some of the things we are doing, and we're planning to do in Chile to follow up on some of those ground-based experiments in the next couple of years. So we it's great to go to space to study the early universe. It's a very clean environment. The problem with going to space is it's really expensive to launch big things into space. And often you can do some version of what you'd like to do on the ground, and when you can do that, you try to do that. So we want to go to an environment that's as close to space as possible, So the two places we like to go to do this work is the South Pole, which is very cold and dry. And the other very popular site is the Atacama Desert, where we go in the mountains in Chile to this remarkably dry environment in the Atacama Desert. The Atacama Desert's an incredible place. It's also where one of the optical telescopes you saw is located. There are parts of the Atacama Desert where it has not rained in recorded history. You know, and I remember going to a restaurant, talking to the waiter and saying, "Look, there's no roof here. Does it rain?" And I said, "Have you ever seen rain?" He said, "Yeah, I went to my cousin's wedding in Santiago, and it rained." So I know in California, I'm from the East Coast, you guys don't get as much rain as you like sometimes. Try the Atacama. But for astronomy, this is a remarkably nice, good thing to be in a place like that dry. The sites we go to aren't perfectly dry. You can see even some clouds here where we are. We like to be at high altitudes. Here we are about 17,000 feet. We actually get winds coming across Bolivia sometimes that pick up humidity over the Amazon. So we'll even occasionally get at this particular site because there's a lot of snow. But it's a very good place to be. It's comparable to the South Pole in terms of its performance for doing the kind of work we want to do. And it's much closer to good restaurants. There's a nice place to eat within an hour and a half away. Perhaps more importantly, there's an airport 2 hours away. So you can actually fly back and forth from the US in 24 hours, which makes it a much easier place to work. When we do these things, we have these big collaborations. This is our collaborative banner. We've got now 30 institutions involved all over the world. It's actually really exciting to be part of something that's international, to be working with colleagues and be part of a broader community of scientists. This is how we do things best. Here's just some of our team at a recent meeting. And, the only disturbing thing is they all keep getting younger, just like the undergraduates. Except for a few people keep aging, like my friend Arthur Kazowski in the front. But it's great to work with a team like this, and whenever you see results from something like this, it really is a product of a whole team of people working together. So what we want to do is, these are the maps I showed from the Planck Experiment. This is just one piece of the sky. We go in, and we zoom in at higher resolution, and we get more detailed maps, not only the pattern of temperature, but as I briefly mentioned, polarization. Light is polarized. We can think about light as an electromagnetic wave propagating towards you either with the electric field pointed this way, that's one polarization, or maybe pointed this way, or this way. There are different ways you can orient it. The light coming off that lamp there is unpolarized. There's equal number of electrons coming towards us, photons coming towards us with each polarization. But when light scatters, it tends to scatter in one particular polarization. I'm sure almost all of you have gone to the beach and noticed that there's a lot of glare coming off the ocean. That's polarized light scattering off the ocean. When you put on your polarized glasses, it blocks light coming in this polarization and only lets light coming in this way. You can do an experiment next time you're at the beach. Take your polarized glasses, close one eye, rotate them 90 degrees. You'll discover not only do you look stupid, it works terribly. It's letting in only the mostly scattered light, and makes the glare worse. So always wear your glasses properly. I got in great trouble 2 nights ago teaching a friend's kid. Always drink from the bottom lip of the glass. Never drink from the top lip of the glass. Okay? hadn't occurred to this 5-year-old before. Fun games to play with kids' friends, especially when your kids are all in their 20s and not vulnerable to this. Yeah, so what do? Right now, we're looking at this data not just in temperature, but in polarization. And we'll be able to measure those basic parameters again as precisely as the Planck experiment by looking to smaller scales. So what we're in the midst of doing right now is we've got this quality data, higher resolution, over about half the style. And it's all sitting on computers and our team's looking at it. And we're working to make more accurate determinations of the parameters. Now, how do we do that? I'm going to tell you about process because I'm not going to tell you the answer. And the reason I'm not going to tell you the answer is I don't know it yet. Right now, we're doing something we call a blind analysis. So we sat down, and this is one of our colleagues based in England. She came, who wrote out an email saying, "Here's our summary. Here's our plan for how we do the blind analysis. We write down all these things we will do, where we will test the data, make sure that it's consistent, it's behaving in a way that isn't surprising us." So what we do in practice actually is we take our data measured on Mondays, every Monday's data, every Tuesday's data, every Wednesday's data. We don't look at those data separately. We look at the difference between Monday and Tuesday. That contains no information about the early universe. It just should be a map of our noise, because the sky should look the same Monday and Tuesday. And we check that that's true. And then we divide our data in other ways. Let's take data when the moon is up, when it's not. Let's take data when the atmosphere is a little worse, when the humidity is a little higher. Take that half of the data when the humidity is bad, and the data when the humidity is low. Make sure that humidity doesn't change things. Make sure that the temperature doesn't change things. Do all these what we call null tests. And we don't look at the results until we convince ourselves we passed all the null tests. So we write out this plan, and actually here we are. This is a group gathered at my institute in New York. And the important thing, well, it's good to see the people who do the work and the person who pays for the food. And we write on the back, here's what we're going to do. And we're not going to let ourselves look at the results until we've passed all these tests. And this is an approach that I think is very important to do in almost everything. I mean, there are studies where people take, you give someone a political proposal and you then tell them, oh, the Democrats support this. Now they either support it or they don't. Or you make your decisions based not on the data, but on what your belief system is. And we don't, as scientists, we don't want to, I think some of us would like to see, I think there are people who like to clean things up and people who like to make messes. So some of us would like to see our results come in, confirm the results from the measurements from the Hubble telescope at distance, suggest that there's something wrong with the other experiment, and that everything fits together. And others would like to confirm the Planck experiment, and for there to be this intriguing tension, and there, evidence of new physics. And we don't want to be persuaded by what we want, but by the data. So that's what we're working on now. And then what we're looking forward to, and this gives you a sense of sort of the process of doing these things. You're working on analyzing one set of data, and you're building your next experiment. And the next experiment we're building, so here is our site in Chile where we've got our telescope, this is an experiment led primarily out of Princeton and Penn. And this telescope in the foreground is from a group led out of UC, primarily out of Berkeley and San Diego. And what we've done is we've gotten together, formed one big team, and with the help of the Simons Foundation, we're going to build an array both of big and little telescopes that we hope a little bit further down over there. And here's the team coming together to at a meeting in San Diego last year. I'll be heading from here to San Diego to talk to some of the folks involved. And we're going to build a whole set of new sites. Let's see, do we have, I think, simulations now of where the telescopes will be in the foreground. And we'll be measuring at even higher precision. And we'll actually have two primary goals. One is studying the fluctuations to get a better determination of cosmic parameters, to understand the properties of the universe today. But the other piece is to perhaps get some insight into this question that I alluded to earlier: what happened very early in the history of the universe? Did the early universe undergo a bounce? Were the fluctuations generated before the universe, the Big Bang, in which case we should only see fluctuations in temperature, no gravitational waves in the very early universe? Or did the very early universe undergo this very rapid period of expansion that we think generated the fluctuations, an idea called inflation? In that latter case, we should see gravitational waves. Those should reveal themselves through a pattern of polarization. Now, there was actually a claim a couple years ago that these were seen. Unfortunately, they turned out not to be real, but just that smudge in the window. It was just due to emission from our galaxy. So we're continuing to work hard, look for these gravitational waves, use them to look at large-scale structure. And that's sort of where we're going next. The results I talked about that are underway, we hope to report by the end of the year, but the end of the year is fast approaching, so we'll probably report early next year. These new experiments we hope to get running in the early 2020s. And I'm going to skip ahead of the details and conclude so we have more time for questions. So, what should we take away from this talk? A couple things. The biggest point is if you look at the big picture, and this is something Todd already summarized in the introduction, the universe is really simple and really straight. That we have a model that seems to fit most things, fit almost all the data, but we'll go back, refresh you on the almost. And we've measured that case, the basic parameters of the model to high precision. But as our data improves, it looks like everything doesn't quite fit together. Sometimes it feels like you've assembled a puzzle, and you've probably all done this, and you've got like a few pieces left over, and it looked like everything fit, and maybe there's something not quite right. And that's sort of where we are at the moment. And do we just have to remove a few things and move them around? Is there just something wrong with the data we have? Or is there some bigger piece missing? And we don't know yet. And that's what makes things so exciting. And what we're doing to advance this is we're getting more data. We're getting more data in the microwave background. We're building telescopes to succeed the Hubble telescope that will give us even more precise measurements of the expansion rate of the universe and how it evolves with time. We're building successor telescopes on the ground. And with all these pieces, we're hoping to understand where we came from and where we're going. So let me end there. for some questions? Let's see, do people do have a mic, or do people who just have questions want to yell? Yeah.
How do they measure the millionths of degree changes? What instruments are used? Or?
So how do we measure these tiny fluctuations in temperature? Many of the things we do now use what's called a bolometer. Bolometer measures how much energy comes in. So we have a radio telescope that brings the radiation to a focus, to an image. And rather than having something like on your camera, your phone camera, or in an optical telescope, which is a camera made of detectors that detect photons by producing electrons, called CCDs. Those are the detectors in your camera. We have detectors that the photon comes in and deposits a little bit of energy. And the type of detectors we use primarily are transition edge sensors. They make use of the properties of, if you make something really cold, it becomes a superconductor. So you can make something, make it really cold, make it superconducting. You deposit a little bit of energy, this tiny millionth of a degree of level of energy. It heats it up, makes a transition from superconducting to the normal state. A superconductor doesn't let a magnetic field through. Something that's a conductor does let it through. So it undergoes that transition that produces a current. We detect the current. Now, when we started with this, we would have experiments like the WMAP experiment. It only had, actually, different detectors, and actually less sensitive detectors than transition edge sensors. It only had in the experiment 20 detectors. The Planck Experiment had about 100 detectors. Right now, this next generation ground-based experiment has an array of about 10,000 detectors. So that enables this enormous increase in sensitivity. That, of course, changes the way you build them and analyze them. When we had a handful, I knew each detector. Each one had its own quirks, and we all went and understood it. When you have an array of 10,000, you have to treat that data very differently and use different techniques to understand what's going on. We build an array of these detectors, and these are developed, as you saw all these people in the pictures, that's because you have some people who build the detectors and others who build the electronics. Others who build, this has to be very cold. In order to have this high sensitivity, you operate these at temperatures a few thousandths of a degree above absolute zero, maybe 50 millikelvin. So you have people who build the doers, they're going to keep things nice and cold. People who build the radio dishes and the electronics to control them. You saw pictures of some of the people from our group who do the computer analysis. So all these, you need all these different people with these different expertises to come together to make something like this work. Yeah.
Is the background radiation equal everywhere in the universe, or is it lumpy?
So the question is the background radiation equal everywhere in the universe, or is it lumpy? It's almost equal, but what we see in the sky is actually the lumpiness. So the pictures I showed you is the fact that we see it's a few millionths of a degree colder there, a few millionths of a degree hotter there. Now, something you might wonder is what would we see if we were standing somewhere else in the universe? We can actually measure that indirectly through a neat effect. So let's say I have a cluster of galaxies here. That cluster is filled with hot gas. That hot gas has lots of electrons in it. The microwave background hits the cluster and scatters to us. So I get to see coming from me over there light that came in this way and headed out here. So I actually can measure effectively what is the average temperature that this cluster sold. And that effect, called this in the ISL-Dulwich effect, after two Soviet physicists who first pointed this out, is something we see and measure, and we can use its amplitude and how it behaves to show us that not only do we see a nearly uniform star, but clusters of galaxies billions of light years away see the same uniform temperature that we do. Over there?
I love your models of the evolving universe. They look really beautiful, and they kind of look much like what we're seeing with the Hubble and the beautiful images of the structure. Do your models take into account matter and antimatter? Is that part of the story, or is it just normal matter that's evolving?
So our universe, for some reason, we don't understand, has a little bit more matter than antimatter. So the universe starts out with about 1 billion antiprotons, about 1,000,000,001 protons. Well, equal amounts sort of make sense, because when photons annihilate, they'll produce both protons and antiprotons. But we have some physics in the early universe that produces this baryon asymmetry. We have a couple ideas on what causes it. They tend to be connected to ideas in how we unify forces together. They motivate some of our ideas for looking for physics at very small scales of places like the Large Hadron Collider. One of the wonderful things is this connection between physics, the very small, and the universe as a whole. So we see our universe is mostly matter, or very little antimatter. Now with the simulations, actually, those simulations only trace the effects of gravity and matter. Since I'm director of a center that's computation and does simulations, we have lots of people who their scientific research is let's put in the effects not only of gravity, but of pressure, of star formation, of, as you'll hear next week, Andrea Getz will tell you that there are these huge black holes, millions of times bigger than our sun, lurking in the centers of galaxies. They affect the environments around them. To get all the details right, you want to include all that physics. Those tend to matter on the scales of only 1 million light years or smaller, which as a cosmologist is small. When I look at the very big picture for large-scale distribution of galaxies, we can get away with doing this with just gravity.
Could I just follow up one more?
Yep.
Do you think there are antimatter stars?
No.
No?
And the reason is, the question is, are there antimatter stars? Or are there, another version of this is, are there parts of the universe that is more antimatter than matter?
Well, there's fluctuations, so could you imagine? Yeah.
So if there was, then there'd be a boundary between regions that had more antimatter and regions that were more matter. In that boundary, there would be lots of annihilation. The matter would collide with the antimatter and release energy. That would produce fluctuations in the pictures you saw. Because there'd be regions that were these hot strips that were boundaries between matter-dominated universes and antimatter, matter-dominated bubbles and antimatter-dominated bubbles. And we don't see them. And we can use the fact that we don't see them to constrain fluctuations in the matter to antimatter ratio. So, those are scientific papers that people write and they look at those constraints to answer that question.
Okay, let's thank David once again.
As I said, he'll be available in the lobby for a while if you want to chat some more.